Assalamualaikum warahmatullahi wabarakatuh. My name is Siti HANANI binti SIDIK. We are from Group 2. So today I'm going to present on the topic of electrolytes. So first is the various types of working electrode. So working electrode, in a corrosion testing, working electrode is the sample of corroding metal. So the working electrode uh, can be bare metal coated, and also the working electrode can be referred either cathodic or anodic. So the function of working electrode, the fixed potential difference will be applied between working electrode and reference electrode. So this potential will drive the electrochemical reaction at the working electrode surface. As you can see from this picture, so here is the example of working electrode. Here is the sample which will act as the working electrode. This is as the reference electrode and the counter electrode. This working electrode can be either cathodic or anodic. So the current produced from the electrochemical at the working electrode will be balanced by a current flowing in the opposite direction at the counter electrode. The reference electrode acts as a reference point, and the current resulting from the electrochemical reaction will be amplified and plotted as a function of time. The various types of working electrode, we have three types of working electrode. First is materials utilize carbon, which is the carbon-based working electrode, including that made from glassy carbon, pyrolytic carbon, and porous graphite. Third is working electrode can also made up from varieties of alloys.
Okay, hi, my name is NURALYSA SYUHADA binti ISMAAD. My metric number is 194357 and I will present about reference electrode. So what is reference electrode? Reference electrodes are electrodes that have a stable and well-known electrode potential. The basic function is to maintain a constant electrical potential against which deviation may be measured. So the desirable characteristic of reference electrode, that reference electrode should be fast, it should be easy to construct, and it should develop potential which are reproducible even if small current are passed. Okay, so the ideal reference electrode, it must reversible and obeys Nernst equation. Must exhibit a potential that is constant with time, return to its original potential after being subjected to small current. Next, there are many examples of reference electrode, and one of it is standard hydrogen electrodes, or we call SHE. It is a primary reference electrode and it composed of an inert solid like platinum on which hydrogen is absorbed. Half cell, as you can see, the half cell reaction is half plus H plus E come H half H2. The potential value is 0 volt. Okay, next we have saturated calomel electrode, SCE. It's a much more common reference electrode. The electrode is coated with Hg2Cl2, with calomel Hg2Cl2. The electrolyte is a solution of saturated potassium chloride. Okay, the chloride is used to maintain constant ionic strength. So the half reaction is Hg2Cl2 plus 2E become 2Hg plus 2Cl minus. The potential value is plus 0.44 volt. Okay, next we have silver chloride electrode, AgCl. It composed of silver wire that has been coated with silver chloride. It immerses in the solution that is saturated with potassium chloride and silver chloride. The Hassassan reaction is AgCl plus E equilibrium Ag plus Cl minus. The potential values plus 0.199 volt. Okay, next I will pass to my friend.
Hi, I'm MARYAM binti HASSAN. My metric number is 194718. Now I'm going to explain the pretreatment of electrodes. So the first one here is the carbon electrode, which is the glassy carbon. The first pretreatment here is mechanical polishing. So mechanical polishing here that can be used is by using alumina on a smooth glass plate, and the alumina is slurried in ultra-pure water to make a paste. And then using circular motions, the electrodes are polished with an even force applied starting from the largest grid size, and then the electrodes are carefully rinsed and with pure water, and then followed by the ultrasonication in the same medium for about 15 minutes. So the second one here is solvent cleaning, usually applied in conjunction with mechanical polishing, and this solvent cleaning activates GC without introducing new microstructure and surface chemistry. And this works by dissolving and or desorbing adsorbed contaminants from the surface, generating clean edge plane, i.e. the active sites. So these acetonitrile, isopropanol, and others can be used as solvents, and these solvents should be purified before using to clean the electrodes. So the third one here is heat treatment. The heat treatment cleans the surface by dissolving contaminants from active sites, and it creates a low oxygen surface by decomposing the carbon-oxygen functionalities as carbon monoxide and carbon dioxide. And it generally doesn't alter the surface morphology or microstructure, and it is best performed under high vacuum conditions in these pressure. Uh, and this heat treatment is carried out by heating the electrode to about 500 degrees Celsius in the absence of oxygen, and, and it is effective to dissolve contaminants. The second one here is polycrystalline platinum and gold. It's a type of metal electrodes. So the first one, same as GC, mechanical polishing, which is a similar process as mechanical polishing for the BC, of course. And then the pre-treatment of the platinum and gold often involves two steps. First being polish, and then followed by either laser irradiation, vacuum heat treatment, solvent cleaning, or electrochemical polarization. So the second one here, same as before. Solvent cleaning, usually use this one, we only use this stilt and AC clean isopropanol or dichloromethane. So the electrode is soaked in warm ultra pure water for about 30 minutes to complete the solvent cleaning, and in some cases maybe simply prolonged exposure to an acid is sufficient to clean metal surfaces. So the third one here is street treatment, and it is conducted in high vacuum at this pressure as well, at 400 to 900 degrees Celsius. The third one here is semiconductor electrodes, which is ITO or indium titanium oxide. First one is solvent cleaning. It is carried out by soaking the electrode for 20 to 30 minutes in isopropanol, then cleaned by distillation and exposure to AC. This one is effective at cleaning the surface without causing any roughening, bulk oxide reduction, or microstructural damage. So, washing the ITO surface with a solution of Triton X 100 is surfactant and water, and it is followed up by ultrasonic washing in ultra-pure water and ethanol for at least 10 minutes each. So the second one here is a bit different from the previous ones, which is the radio frequency plasma treatment. This can be used as using a standard Herrick plasma. using a cleaner model PDC 32G at 60 watts and 100 to 200 milliliter for 15 minutes. So this one samples should be solvent clean first as the above right here. So the third one here is pre-treatment performed in a vacuum relatively free of residual oxygen and in relatively low temperatures should be used to avoid dissolving the ITO film from the substrate or decomposing it.
So I will proceed with the next part, which is about the properties and functions of electrolyte. Electrolyte is a chemical compound that dissociates into free-moving ions. These free-moving ions can be cation or anion that are capable of transporting electric charge. As a result, these free-moving ions can conduct electricity in molten or aqueous state. Example of electrolyte is sodium chloride solution. The functions of electrolyte: firstly, the electrolyte completes the electrical circuit and it also acts as a medium for charge transfer, which means that when the electrolyte dissolves in the solution, it produces these free-moving ions, and due to its free-moving properties, it is able to transport the electric charge throughout the medium. Therefore, it enables them to conduct electricity. Electrolyte is also used to maintain the electrical neutrality through the salt bridge. Moving on to the next slide, which is about the properties of electrolyte. So electrolyte can be divided into two: a strong electrolyte and a weak electrolyte. For a strong electrolyte, the properties are completely ionized in water, meaning that there is 100% dissociation in water. And due to 100% dissociation, it contains only ions. There are no molecules of the electrolyte because all the molecules of the electrolyte has been dissociated into free-moving ions. So all ions are present in the solution. Therefore, it is a good conductor of electricity. Example of strong electrolyte is strong acid, strong bases, and also soluble ionic compounds that are soluble in water. For example, like hydrochloric acid, potassium hydroxide, and also sodium chloride. Weak electrolyte is the other way around because it partially ionizes in water, usually 1 to 10% dissociation. Since it's a partial dissociation, it contains both ions and molecules of electrolyte, because only a very few molecules of electrolyte has been dissociated into ions. The rest are still remaining as molecules. So very few ions are present in the medium, therefore it is a poor conductor of electricity. Examples are weak acid and weak bases such as ethanoic acid, hydrofluoric acid, and also ammonia. That's all from me. Thank you.
Assalamualaikum and hi, my name is HIDAYAH. My metric number is 194777. So I will continue the presentation based on the properties and functions of the supporting electrolyte. So what is supporting electrolyte? So supporting electrolyte is that the electrolyte that contain non-electroactive species with an ionic strength. And the conductivity is much greater than the electron species applied to the electrolyte. So the example of the supporting electrolytes that we usually use is KCl and also KNO3. So the first properties of the supporting electrolyte is the medium must contain mobile ions between the electrode in electrochemical cell. Why? Because we want to allow the measurement of the electrode potentials. The second one is the medium with good solvent strength. This is to dissolve reactants and products from the electrode reaction. The third one is a medium with low reactivity, which is to be compatible with oxidizing and also electrode reduction. And then we go to the functions of the supporting electrolytes. So the first one is to provide the counter ions for the analyte. The second one is to carry the electrons from the analyte to the electrode surface. Next is
carry the charge to the solution to limit migration effects, and solubilize analyte to make a homogeneous solution. So I will pass the presentation to the next presenter.
Thank you, Hidayah, for your presentation. And now I will continue with my presentations on properties and functions of solvents. Okay, as we know, solvents is the substance in which the solute is dissolved, for example, water, ethanol, and toluene. There are three properties of solvents, which are: first, nonpolar solvents. Nonpolar solvents which contain bonds between atoms with similar electronegativities, such as carbon and hydrogens. We can think of hydrocarbons, such as gasoline. The second one is polar aprotic solvents. Polar aprotic solvents may have hydrogens on them somewhere, but they lack of OH or NH bonds, and therefore cannot hydrogen bond with themselves. For example, acetone and ethyl acetate. The third one is polar protic solvents, which have OH or NH bonds. This is important because protic solvents can participate in hydrogen bonding, which is a powerful intermolecular force. Additionally, these OH or NH bonds can serve as a source of protons, which is known also as H+. Next, I will explain to you about the functions of solvents. First, it can speed up or slow down the reaction, which means if you mix water with sugar, you can speed up the dissolution of sugar in the water. Second one is help to make up the structure and determine their stabilities. And the third one is help to determine the shape of large molecule like protein. So I will pass my presentation to the next presenter. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is NURUL. ZAINAL. My metric number is 194359. Today, I want to present about what to consider choosing an electrolyte. Okay. So the first one is conductivity. The second one is chemical and thermal stability. The third one is solubility. The fourth one is mobility of active species, temperature, viscosity, and also electrochemical stability. Okay, so basically choosing electrolyte is a current that's carried by the movement of ions and not the electron. So basically for conductivity, we need electrolyte that have the higher conductivity, as it can easier for the movement of ions. And then for chemical and thermal stability, we need higher chemical and thermal stability, as we need to increase the energy or voltage supply for the current to move. And then for solubility, we need high solubility, as it can give a strong interaction with the ions. So the next is mobility of active species. For mobility of active species, we need the high concentration of active species, as it can dissolve in the electrolyte, so make it the movement of ion increase. And then for temperature, we need the high temperature, as the kinetic ions can move faster. And for viscosity, we need a low viscosity, as for the ion to diffuse faster. And for the last one is electrochemical stability. We need a high electrochemical stability, as to supply the voltage for the current to carry